Okay, so the plan for today is to go over Bayes' theorem. Um, and this is kind of a topic that can range from just a little short note about, some little like practical tool in probability up to really, an entire course or even an entire field of study. Um, and I think we'll see some of that nuance today. So we're gonna take, about a class period to cover Bayes' theorem. I typically take somewhere between 1 and 2 class periods, so we might spill over a little bit um, into next class with Bayes' theorem. There are some supplements posted on Blackboard because I'm planning to go a little bit further into it than what I think the book kind of naturally goes into. So I've posted a couple supplements on Blackboard. Um, and the homework I think should be available. I'll check after class today and make sure it's available. Um, Also note that I think I mentioned this last week as well, but the Examity practice exam is available. Um, most students have been able to get on and kind of get Examity up and running, but occasionally there are some, tech challenges with things like enabling access to, microphone or something like that. So I would recommend getting on quickly, not, sometime maybe this week. And, you know, uh, going through Blackboard, logging onto Examity, getting your account set up, making sure that all of the tech is working right and all of that. I'd recommend doing that well in advance of exam two. We do have a little ways before exam two. Exam two is not until the week of November 11th, but again, I would recommend getting this knocked out pretty soon. That way, if anything does go wrong, it's easier to get it sorted out now than say the week of the Unit 2 exam. And I know that the 11th is a little bit of a ways away, but um, at some point I'm going to stop reminding you about this every day, and we don't want to forget about it. And then just remember the week of exam week. And the quote of the day is kind of I guess, more of an idea of the day today. Something like, "Don't underestimate the impact of survivor bias." Um, and this kind of came about. Well, this kind of came about or popped up in my mind over the weekend or last week. Um, I saw one of those YouTube shorts every once in a while, click on a YouTube short. I try not to watch too many short things like that and, destroy my attention span. But I clicked on one and basically it was talking about Arnold Schwarzenegger's workout program where he was like talking about like a shoulder workout day that he would do, and he would do like 35 sets of exercises or something insane. And a lot of the comments were interesting. There were people who, Arnold came out and like basically came out with a book and said like, "This is my workout plan" or whatever, and people would try to emulate that, right? Um, and most of these people in the comments were like, "Yeah, I tried to emulate his workout program, and like I ended up getting injured all the time, or I ended up just being so fatigued that I like couldn't do anything else in life, or it just didn't work for me, or I couldn't recover fast enough, or whatever." And um, even setting aside, what we might say is something of a pharmaceutical enhancement or something along those lines. Even setting that aside, we have to take into account when we're looking back like that, when we're looking at somebody like Arnold and saying, "Hey, he had a great physique. How do I get that physique?" Or when we're looking at somebody like Robert Kiyosaki, who wrote the book Rich Dad, Poor Dad, uh, he had a great financial outcome. How do I get that financial outcome? Whatever it may be, if we're looking backwards at successful people and saying, how did they become successful? We have to remember that there's a survivor bias there. So like Arnold's workout program, there were probably 1,000 people kind of like Arnold who tried to do a workout program kind of like Arnold's, and 999 of them kept getting injured or had too much fatigue or couldn't recover or whatever. And the one of them that was the survivor that succeeded was Arnold. So if you try that, you don't really see the failures so much as the successes. You're probably more likely to be in that 999 and it not work for you than to be in the one out of 1,000. Or the same with Robert Kiyosaki with his book Rich Dad Poor Dad. I mean, it's a great book. I would recommend everybody read that book. And then alongside it, read like Dave Ramsey's Financial Peace University, just taking two extremely different views on things like debt and the way to use debt in your life, and the way to run, kind of household finances, to kind of opposite ends of the spectrum. And then you can kind of see, both points, and then probably pick up a path, maybe walking somewhere in the middle between those two. But Robert Kiyosaki, in a very loose sense, his financial strategy was buy a bunch of houses. This was maybe back in, I want to say maybe the 80s or 90s. Buy a bunch of houses, get yourself into a huge amount of debt, and then you have this like pressure, this weight of the world on you that you have to pay off all this debt, and that will like spur you to creativity and innovation. And it's like, yeah, that worked great for him, but a lot of people will just crumble under that pressure and, have a nervous breakdown. So it doesn't work for everybody, right? He was the one success story, but there were probably 1,000 people who tried that, and probably 999 of them who it was not successful for. So do you want to really walk in his footsteps, or something a little more middle of the road? And as kind of a general idea, the end result of, pretty much anything is dependent on kind of three things: systematic effects that are uncontrollable. So things like, maybe in Arnold's case, like genetics, or in Robert Kiyosaki's case, like, what was his family's background? Did his family have seed money to give him or not? Things like that. Controllable systematic effects. So things like, maybe what was Robert Kiyosaki's education, right? What was he doing? Or what was, Arnold's workout program that he chose to do? And then also something that we, neglect is chance or luck, right? Uh, Arnold was maybe lucky that he never, got a little bit out of sync in a heavy lift or something, and blew out a joint, and, was had a problem with that for the rest of his life, or that messed up his career or something, right? So there's going to be luck also in the, top 1% of 1%. There's going to be a good deal of all three of these, and of course you can control kind of one of the three of them. So focus on what gets you the biggest bang for your buck as far as controllable systematic effects. What choices can I make that minimize the effect of the uncontrollable effects, and maybe to an extent minimize the effect of chance or luck, and give me kind of the value out that's related to the effort I put in. So that's kind of the idea for today, is that the ideas of survivor bias and similar ideas, are quite important, especially when we're looking backwards at success stories. You always hear these people say, pick up, a biography of somebody who's super successful in a field you want to go into. Yeah, that can be, yeah, inspirational, but it probably shouldn't be aspirational. You shouldn't say, I want to do everything. I'm going to start at page one and set up my life to look like their life. That might not be the right approach. Okay, so that was the idea for today. And we're now moving on to Bayes' theorem. Okay, so let's look at a motivating example to start with. So suppose we have two car manufacturing plants, plant one and plant two. Maybe one of them, maybe these are Ford plants or something, and one of them's in one city, one of them's in another city. And suppose that each plant produces two car types, type 1 and type 2, maybe F-150s and Mustangs, something like that. We'll just call them plant 1 and plant 2, and type 1 and type 2. And then suppose that we say that of the cars produced by plant 1, 10% are type 1 and 90% type 2. And of the cars produced by plant 2, 95% are type 1, 5% type 2. And then suppose that we have cars coming off of these two assembly lines at these two plants, two different types of cars. They get essentially mixed together, and they end up getting sent to a car lot. And we observe a car of type 1 on the lot. So we walk onto a car lot and I see, hey, that's a Ford F-150 I'm interested in buying. But maybe I would like to know whether that came from plant 1 or plant 2, or have an idea. Maybe I heard that there were some quality control issues with plant 1 and not at plant 2, or something like that, right? I might be interested in what's the likelihood that this particular car I'm looking at came from plant 1 versus plant 2. And the question is, what's the approximate probability the car came from plant one? In other words, estimate the conditional probability the car is from plant one, given that I know that it's of type one. Given I'm looking at, say, a Ford F-150, what's the probability it's from the Detroit plant, for instance? Do they even make cars in Detroit anymore? I feel like that probably isn't a thing anymore. But anyway, so if I look at this, my tendency is to say, well, of the cars from plant one, of the cars from plant one, 10% are type one. Of the cars from plant two, 95% are type one. My my tendency would be to say, oh, well, I think that the probability that came from plant one is pretty low, and the probability that came from plant two is pretty high, given that I know it's a type one car. Or if I was looking at a type two car, and instead I might say I think the probability it came from plant one is high, probably came from plant two is low because of this ratio, this 10 to 95. I look at that and I say, okay, I think probability it came from plant one is pretty low if it's a type one car. Probability from plant two is pretty high if it's type one car based on these numbers. So if you do studies, there was a guy, David, I think was his first name, Grether, who did similar experiments. And that's typically the conclusion people would come to. But the thing is, we have to be actually super careful. Doing such a naive analysis can lead us down an incorrect path pretty easily in some reasonable circumstances. So these aren't circumstances that like never occur in real life, or some crazy mathematician had to come up with some crazy theory to break um, the conclusion. But these are realistic circumstances that come up, and we'll actually see a couple of examples of realistic circumstances in medicine that actually do come up where we have to be very careful with these ideas. So the question is the probability high, moderate, low, or are we actually missing information? Do we actually need more information to know? And actually, the answer is that we need more information. In particular, let's let's take a silly extreme case uh, just for the sake of an example. What's the probability that a car of type one came from plant one if plant one has been closed down for 2 years, right? If it's had some whatever issue, if it got hit by the hurricane or something down south and it's been closed down for a long time, well, now it would be basically zero. Or analogously, if plant two was the one that was closed down, what's the probability that the car came from plant one, given that it's a type one? If plant two is closed down, well, now it's like basically 100%, right? So we can see in these extreme cases where I essentially have zero cars coming from plant one, or I have zero cars coming from plant two overall, these relative proportions of the different types of cars don't matter so much when I have an extreme uh, difference in the underlying number of cars coming from plants one versus two. And so, in fact, maybe we have 90% of all cars that are produced come from plant one. It's just a much bigger plant. It puts out a lot more cars. And only 10% of all cars come from plant two. Smaller plant doesn't put out as many cars. So let's take a look at this. Instead of using probabilities, let's use actual numbers of cars. Suppose there are a total of 200 cars that are made, total between plants one and two. Well, then on average, we would have, oh, let me go down below here. On average, we would have, of those 200 cars, well, 90% of them, or 180 cars, would have come from plant one, and 10%, or 20 cars, from plant two. And then of the cars, let's say from plant 2, they could be either type 1 or type 2. Plant 2 produces 5% of their cars as type 2, so on average that's 1/20th. So on average we would get about one type 2 car out of these 20 plant 2 cars, leaving us with 19 type 1 cars out of those 20 plant 2 cars. And we could do the same thing for plant 1. Plant 1's 180 cars, well, 10% of those would be type 1, so about 18. And the remainder would be type 2, 90%, or that's just 180 minus 18, 162. Now, what am I looking for? I'm looking for probability of plant 1 given type 1. So if I just walk onto the car lot and maybe all the cars are covered in those sheets or something and I can't tell what car is what, and I pick a random car that I don't know what type it is, what's the probability that it came from plant 1 versus plant 2? Well, it's 90% probability it came from plant 1 before I know what kind of car it is. But I pull off the car cover and I see, oh, it's a Ford F-150. I guess I probably should be able to tell a F-150 from a Mustang, even with the cover being on, but whatever. But I pull it off the cover and I say, oh, this one's an F-150. It's a type 1 car. So now I know that I'm only looking at these two possibilities. These are no longer possibilities because I know that the car I'm looking at is a type 1 car. Of the type 1 cars, these 18 and those 19, what proportion came from plant 1? Well, that's 18 of the total number of cars, 18 plus 19. Or this is just under 50%. My calculator is on the fritz right now, so I'm going to use Excel as my calculator. So 18 over 18 plus 19 gives me about 49%. So actually, there's a moderate chance of the car coming from plant 1, given that it's of type 1. And the reason is that although plant 1, the proportion of type 1 cars it produces is pretty low, and from plant 2, the proportion of type 1 cars it produces is pretty high, just the overall number of cars produced by plant 1 is so much higher than plant 2. So plant 1 produces a ton of cars, a small proportion of which are of type 1, and plant 2 produces a much smaller number of cars, but most of its cars are of type 1. So there's kind of two countervailing powers here, right? For plant 1, this number is high while this number is low. And for plant 2, this number is low while this number is high. And those two kind of, in a sense, balance out. I could, of course, have a situation where, you know, one side of things is low and low versus high and high, and then in that case, my gut intuition would end up being correct. But it would end up being correct only because things kind of happen to turn out the right way. So I don't want to rely on gut intuition in something like this. I have to be much more careful. Okay, so what is Bayes' theorem? Well, let me actually make this look a little nicer. There we go. What is Bayes' theorem? It is this statement about probabilities. Probability of A given B equals probability of B given A times probability of A over probability of B. We can think of this, I suppose, two different ways. We could think of this just as the conditional probability statement. We can compute conditional probability this way, and probability of A and B can be split up using the multiplication rule for dependent events as probability of B given A times probability of A. So that's one approach. Another approach is that we can take a look at probability of A and B, and we can realize that probability of A and B, well, the event A and B is commutative, right? A and B is the same as B and A. So I could either write this as probability of A times probability of B given A, or I get the same thing if I exchange the roles of A and B. Probability of B times probability of A given B. And since both of those, of course, are equal to probability of A and B, they're equal to one another. And solving probability of A given B yields Bayes' theorem. And if we use Bayes' theorem and apply it to the probabilities above, we see, well, what do we see? Probability of plant 1 given type 1 equals, so here plant 1 is A and type 1 is B. So that will be probability of type 1 given plant 1 times probability of plant 1, oops, over probability of type 1. Okay, let's unpack this a little bit. One thing that we have to be really careful about is our conditional probabilities. We have to be very careful about what we're conditioning on, right? Probability of plant 1 given type 1 is not the same as probability of type 1 given plant 1. If we're conditioning on the plant and asking of the cars that come out of this plant, what's the probability that they are type 1? That's a different question than asking of the cars that are type 1 on the dealer's lot, what's the probability that they came from plant 1? The other thing we might want to unpack as well, probability of type 1. Let me give myself another line here. So what's the probability of type 1? Well, there are two ways to get a type 1 car. Type 1 and plant 1, or type 1 and plant 2. These are mutually exclusive and exhaustive. Every car of type 1 comes from either plant 1 or plant 2, so it'll be counted either in the first or the second parentheses. And mutually exclusive because a car cannot simultaneously come from plant 1 and plant 2, so the overlap between these two parentheses events will be 0. So then the probability of type 1 is just the probability of type 1 and plant 1 plus probability of type 1 and plant 2. Because those are mutually exclusive events, we can just use our simple addition rule. And then what's probability of type 1 and plant 1? Well, I could split that up either way, but I might as well split it up the way that I have in the numerator here. Right, this numerator is actually just probability of type 1 and plant 1. So when I split probability of type 1 and plant 1 into the product of two probabilities, I'll split it this way. I don't want to split it in a way that gives me probability of plant 1 given type 1. Well, because that's the quantity that I don't know. But probability of type 1 given plant 1, I notice that that is just this number here. I have that piece of information. So I can view Bayes' rule as just a way to flip a condition. This is the probability that I want, conditioned on type 1, but I don't have that information readily available to me. However, I do have readily available information about probabilities conditioned on the plant that the car came from, which I can't seem to select effectively, but I do have this information, probability of type 1 given plant 1. I say I would like to flip that condition around. Instead of plant 1 given type 1, I'd like it to be the other way around, type 1 given plant 1. Those are not the same probability, but I can convert one to the other using Bayes' theorem. And now I've rephrased my my problem in components that I have access to, right? The probability of a car overall coming from plant 1 is 90%. So I put that here and here. The probability overall of a car coming from plant 2 is 10%. So I put that there. And then given that a car came from plant 1, the probability it's type 1 is 10%. So I'll put that here and here, right? That's where I cannot select these conditional probabilities today. That's where this conditional probability and this conditional probability show up. Probability of type 1 given the car came from plant 1. And then probability of type 1 given plant 2. That is our 95% here. That is probability of type 1 given plant 2, this number here. So we see that probability of plant 1 given type 1 is not only a function of probability of type 1 given plant 1 and probability of type 1 given plant 2, right? Our kind of initial gut feeling, just looking at 10% versus 95%, it kind of would be if we had gotten Bayes' theorem, but had ignored this like probability of plant 1 there, this probability of plant 1 there, and this probability of plant 2 there. But in reality, that underlying probability, the overall likelihood that a car comes from plant 1 versus plant 2, plant 1 might be a much bigger plant than plant 2. That does come into play, right? And you see that this low number 10 is kind of balanced out by its associated high number 90. And the high number 95, the conditional probability from plant 2, is balanced out by a low number of 10. The fact that plant 2 is a smaller plant doesn't produce a whole lot of cars overall. And we get the same 18 over 18 plus 19, or about 49% that we had calculated up here. So we could do things in terms of like forcing it into whole numbers of cars, which worked okay for this example, but for other examples might be more cumbersome to do. Or we could do things just completely in the probability world. One little side note, these really should be like 10% and 90% and all of that. But if we think of percent as a unit, I have 2 factors of percent in the numerator, 2 factors of percent here, 2 factors of percent there. So I have percent squared in the numerator, I have percent squared in the denominator. Basically, my percents all divide out. So quite often I just don't write the percentage signs. And I think of the percentage signs like a unit, like it would be, inches times inches, giving me square inches on the top, square inches on the bottom. That makes a unitless quantity. Similar idea here. The percentages, the percent squared, or the 1 over 10,000, if you want to think of it that way, just kind of divides out between the top and the bottom. Okay, so you look at this and from the quote frequentist perspective, the perspective that we're discussing for the vast majority of this course, you say, hey, that's a pretty nice little tool. If I ever need to find a probability where the condition is kind of backwards of the information that I have, I can flip the condition around and rewrite the answer in terms of information that I have access to readily and get my answer. So that's kind of nice, right? And that's one interpretation. We can think of probability A given B as probability of B given A, just flipping the condition around. But these aren't exactly the same probability. Be very careful about that. We need to multiply by a correction factor, probability of A over probability of B, to correct for that. So we can flip the condition so long as we multiply by the ratio of probabilities in that way. Or another way to think about it is we have our sample space here. And if I have event A that, say, is represented by this red square on the left here, and then not A would be like the right side of this rectangle that's not in that red square. And then I have event B that's represented by the blue blob in the middle, and then not B would be the outside of the blue blob. I have probability of A given B. So in other words, given that I'm in B, so of the outcomes in B, what proportion of those are also in A? So it's the red shaded area divided by the blue shaded area. Okay. That's what I have on the left-hand side, probability of A given B. On the right-hand side, probability of B given A. Now I'm saying, given that I'm in the red shaded area, what proportion is also in the blue shaded area? My kind of overlap shaded area doesn't change, but the kind of like the basis changes, right? Whether I'm looking at my denominator being the blue shaded area or the red shaded area for like the overall. And that's all that I'm doing. I'm just switching what ends up in the denominator. I'm getting rid of one and putting in the other denominator is all that I'm doing in this ratio here. Okay, so it's, the frequentist perspective, it's a cool little probability tool. It warrants about, a half an hour of discussion and a few examples, and that's about it. But there's a whole other perspective on this. And this is what's called Bayesian statistics. It's kind of an entire different, I don't want to say an entirely different field of statistics, but it's a different perspective on statistics. It's a different philosophy on probability. So first, I want to note that nobody disagrees. I mean, the frequentists and the Bayesians agree with this statement. They agree that this is a theorem in probability. Okay, great. It is what it is. They don't disagree with the underlying mathematics. But where they disagree is kind of like we have this mathematical structure we built up, but we don't want to just sit here, kick our feet up on the couch and think about this mathematical structure all day. Like, okay, there are some people who want to do that, but most people don't want to. Most people want to say, all right, I've learned this thing about probability or statistics or something. Now tell me how I can use it in real life, right? Tell me how I can use this to make money or to make better decisions under uncertainty or to make better healthcare decisions for my patient or inform them how to make better decisions for themselves or something like this, right? Or decide whether this drug or that drug works better or whatever it may be. So when I take this mathematical model where there's, let's say, roughly speaking, no disagreement, and I say, okay, here's what it means in the real world, that's where we have a philosophical question. What does probability even mean in the real world? Well, the Bayesian would look at this and say, well, the reason that Bayesian statistics is kind of named after Bayes' theorem, and maybe a side note, the great irony of this is Thomas Bayes, I think he was like a reverend or something, or Reverend Bayes or whatever. I think he like wrote this in some random papers of his or something and like was like, oh, this is a cool little thing. And, I don't think he even published it maybe, or like maybe he told a friend or something. I don't know what, it wasn't like a big deal. And now there's like an entire branch of statistics named after him because of this idea. So you never know what you're going to do during your life that, 200 years later is going to like change the world. So what is the other perspective other than, hey, it's a cool little probability tool that's helpful in some cases? Well, the other perspective is this. We started with probability of A, and we did some stuff to turn it into probability of A given B. So up here, we kind of like converted probability of B given A into probability of A given B. We switched the condition. But down here, I mean, it's the same mathematics. I'm just writing the products in a different way. But we're thinking of probability of A converting into probability of A given B. We're thinking of an unconditional probability turning into a conditional probability conditioned on the occurrence of event B. The Bayesian would say that probabilities represent a worldview, right? The frequentist would say that probabilities represent something like a long-term average. So the frequentist would say, when you say the probability of rolling a 1 on a six-sided die is 1/6, what you mean by that is if you actually constructed a sample of, say, 10,000 die rolls, and you rolled a die, recorded the result, rolled a die, recorded the result, and so on, you counted up the number of times you rolled a 1, you divided that by 10,000, we'd expect that sample ratio, that sample proportion, to be pretty darn close to, say, 16.7%. Or I'd expect you to roll pretty darn close to, say, 167 ones on 1,000 rolls. That's what the frequentist says. But the frequentist, and that's very sensible. But the frequentist is leaning on the ability to repeat a probability experiment lots and lots of times. The Bayesian would say, well, when we're making decisions under uncertainty, a lot of times we can't do that, right? If I say, whatever, you have, you got the flu, you need to decide whether to do this treatment or that treatment, right? And maybe they're mutually exclusive, right? Do you lay down and do nothing in bed for 3 days? Is that going to get you better faster? Or do you get up and keep moving around and, keep the blood flowing and all of that kind of thing and not do anything super strenuous, but don't just lay in bed? Well, you have to decide. You don't get to, hopefully you don't get to have the flu 10,000 times and, kind of average your results together. The Bayesian says, like, you have to make a decision now. You get one shot at it. What are you going to do? You don't get to average together 10,000 outcomes. So the Bayesian would say that something like probability of A represents a worldview. What's the probability that I get better or get better faster or in under a certain amount of time, whatever, if I do this thing versus if I do that thing? I have a degree of belief that if I do this thing, I'll get better versus if I do that thing, I'll get better. So the probability that, let's say, that A is the better treatment than B, or sorry, that A is the better treatment than not A, that's what I assign to probability of A. My degree of belief is going to be subjective, which is the huge criticism of Bayes, or one of the criticisms of Bayes, that my degree of belief that this treatment is better is probably going to be different than yours because I'll have done different research, I'll have had different inputs, I'll have had different life experiences, and so on. So the degree of belief that I assign to A being the better treatment than not A is going to be different than yours, and ours will be different than somebody else's. But what does Bayes say about worldview, though? It says, okay, right now I have worldview probability of A. Based on the information that I have at this time, I think the likelihood that treatment A is better than treatment not A is whatever, 75%. But then I get a new piece of information. Namely, I get a piece of information B. A new paper has come out, or I go to the doctor's office and my doctor says, oh, don't do that. That's silly. Do this instead, or whatever. I get a new piece of information I didn't have before. Now, the question is, how do I incorporate that information into my worldview? Well, I could take one of two extreme approaches. I could either say, throw out all of the information from before, forget everything that I knew throughout my whole life, and just latch onto this. So my doctor said that this treatment is better than that. Well, I 100% believe that this treatment is better than that, and I just do this treatment now. That's probably not a very sensible thing, right? If I have a lot of life experience, a lot of information has gone into my worldview, tossing that all out because of one new piece of information seems pretty flippant. I probably don't want to do that. But on the other hand, I don't want to just say, well, this new piece of information came in, it doesn't agree with my worldview, I'm just going to boot it out and ignore it. I probably don't want to do that either. Although Festinger's theory of cognitive dissonance says that that's kind of more or less what we actually do, unfortunately, but I probably don't want to do that if I'm being careful about things. So I don't want to disregard new information completely. That would probably be silly and not really evidence-based. I also don't want to just be buffeted around by every new piece of information I get. Eggs are good for you. Okay, the only all that I eat for breakfast, lunch, and dinner now is eggs. Oh, eggs are bad for you. Okay, I throw out all my eggs, never eat them again. Or, oh wait, another thing came on and said eggs are good for you again. So now I'm back to my all eggs diet, right? I probably don't want to do that either. So I want to systematically incorporate new information. How do I do that? Well, I take my current worldview, probability of A, I multiply it by this thing, which is sometimes called the likelihood or has a couple of different names. Probability of B given A over probability of B. In other words, the probability of this new information having occurred, given that my worldview is correct, over the overall probability of this new information having occurred. And I use that to update my worldview. I update the likelihood that, say, A is the correct treatment on the basis of the new information B that I've systematically incorporated. I include both my prior probability of A, which kind of encapsulates all of my past knowledge and experiences and so on, along with my new piece of information, B. And I do it in a systematic and methodical way. So that's really the idea of the Bayesian philosophy. Again, it's not, the math here is no different. I just chose to write a fraction in a slightly different way. And these three, so between here, here, and here, this is exactly the same fraction, just written in a slightly different way. But how we're thinking about it when we take this mathematical model and overlay it onto applications in the real world is drastically different between the two perspectives. So again, we don't want to ignore new information inconsistent with our worldview, even though maybe the psychologist would say that that's pretty much what we do most of the time, but ideally we don't want to do that. We also don't want to neglect the experience that we build into our worldview. So from the first point of view, from our cars example, we just look at this and we say, okay, my goal is to figure out what's the probability of plant one given type one. Oh darn, that condition is in the wrong order from the information that I have easily available to me. It would be super nice if I could flip that condition around. Hey, look at that, I can use Bayes' theorem, flip the condition around, and get my answer. That's the point of view of Bayes' theorem from the frequentist perspective. It's a nice little tool that helps us, in some situations, compute conditional probabilities. But the second point of view, in the car example, what does it mean? It means when I walk onto the lot, well, here, let me just keep this up. It means when I first walk onto the lot, again, if all the cars were covered in, those car cover blankets or whatever, and I couldn't see what type of car, which car was which type, I walk up to a car and I say, this car, what's the probability it came from plant one? Well, I know that plant one makes a bunch of cars, plant two doesn't make many cars. So I know that of all cars, plant one produces 90%, plant two only 10%. If I don't know what kind of car it is, I would say the probability this car came from plant one is 90%. I have no more information about this car other than it's the type of, it's the make of car that comes from these two plants. It's a Ford or whatever. And it came from one of these two plants at this proportion. But then the salesman wants to sell the car, so he pulls the cover off and I see, oh, it's a Ford F-150. I now have a new piece of information. I now know that it's of type 1. What is my updated estimate based on this new piece of information that the car is from plant 1? It used to be 90% when I didn't have that information. But now I know that the car is of type 1. I got a new piece of information that came into the fold. How do I incorporate that? I don't want to just jump ship and say, oh, it's definitely from plant 2 because 95% is bigger than 10% or something. I don't want to do that. But I also don't want to ignore the new piece of information that I just got and say, no, still 90% chance of plant 1. This new information does change the perspective. How do I incorporate it? Well, I use Bayes' theorem. My updated probability of this car coming from plant 1, given that I now know that it's of type 1, is about 50%. So it didn't go from 90% to 0. It didn't stay at 90%. It got less likely, but it got less likely in a way that was where we systematically incorporated that information. So we had a worldview when we had no information about the type of car that it was, 90% chance from plant 1. And then when we got more information, we systematically updated our worldview. The new probability it came from plant 1, given that I have this new piece of information, it's a type 1 car, is 49%. And we could imagine chaining this together as well, right? Maybe I then look at the car and notice that it's a red car. And maybe I know that plant 1 produces red cars at this rate and plant 2 red cars at some different rate. Maybe that new piece of information, the color of the car, might be informative. It might maybe bring me back a little bit higher maybe bring my probability of plant one back a little bit higher. Maybe I say, okay, well, plant one produces more of the red cars for this company, so maybe I'm back up to 55%. And then I look and see that it has, this kind of wheels or something, and well, those are more consistent with plant two. So maybe now we're down to 45%, right? Each new piece of information I get, I can systematically incorporate and chain those together and update my probabilities, my worldview, piece by piece as I incorporate new information. So we have these two fundamentally different paradigms, or paradigmata, if you want to use the longer version of the plural. The frequentist versus Bayesian. The frequentist paradigm basically says this is an interesting little tool to calculate probabilities. And they say that, well, probabilities are just kind of long-term averages. If you repeat the probability experiment a bunch of times and you look at average proportion or look at long-term proportions, that's essentially what a probability is. And the Bayesian says this is how you update your worldview about A in the presence of a piece of information B. Okay, so let's look at a couple practical examples. So we're going to use medical testing for a few of these examples. And we'll also see kind of a very basic machine learning model at the end. Okay, so let's look at example one, testing for cystic fibrosis carrier status. So let's first make the assumption that cystic fibrosis is an autosomal recessive disease. Probably a pretty good assumption. All of these genetic things, or really anything in science, is more complicated than our models, but probably a pretty reasonable model for this disease process. And this means that a person needs to have inherited 2 mutant copies of the CFTR gene in order to have the disease. A little side note, this medical background and so on, I'm giving as background, but this isn't stuff that you need to know for stats. So a person with 1 mutant copy and 1 normal copy would not show signs of the disease. They would be called a carrier. So a person can have normal, and they are normal. They don't have the disease, and they also don't carry the disease. They can't, pass on the disease to a descendant. A person could have a normal copy and a mutant copy, and cystic fibrosis has to deal with chloride ion transport across the cell membrane. And usually with things like that, if you can, if this normal copy can pump out enough of the transmembrane protein, then you can kind of get away with having 1 mutant copy that doesn't work so well, because your 1 normal copy can kind of carry the load just fine. This person we call a carrier. They don't exhibit symptoms of the disease. They, their lungs, their pancreas, all the things that are affected by CF look the same as anybody else's. But when they have a kid, maybe their kid or their grandkid or somebody, it pops up as a disease in their kid later on, or grandkid or somebody. Or a person could be mutant, and this is affected, or they have the disease. So these people will have lung problems. They will have pancreatic lesions and all of the things that come with CF. So these are kind of the 3 statuses. I think we all know that, why am I saying normal, or normal mutant? Well, each one of us and the vast majority of cells in our body have a nucleus. We have 2 copies of each gene, right? Each of our somatic genes, each of like the chromosomes. So like 1 came from mom and 1 came from dad. So like if one of your parents passes you a normal cystic fibrosis or CFTR gene, and the other parent passes you a normal as well, you're quote normal. If one passed you a normal and the other passed you a mutant, you're a normal mutant, you're a carrier. Or if they both passed you a mutant copy, then you're affected, then you actually exhibit signs and symptoms of the disease. Okay. Okay. So now suppose that our patient does not show signs of CF, So we presume that he doesn't have the disease. So our patient is not here. But suppose that his brother does have CF. So his brother has two mutant copies. Also, neither of the parents show signs of CF. So after all of this, we can pretty reasonably assume that both parents are carriers. So in other words, like mom is mutant normal and dad is mutant normal. So both parents are carriers. There are some other strange things that can happen, but in the vast majority of cases like this, both parents will be carriers. And what does this mean? Well, if we draw our Punnett square over here, which we might recognize from, I think they usually cover this in like high school science. Again, this is, this genetic stuff, I'm just giving you a little bit of background so you can, so that makes the problem a little bit more interesting, I think. But if mom is mutant normal and dad is mutant normal, if mom and dad are both carriers, their kid could be mutant normal or normal mutant or normal normal or mutant mutant. So this person will exhibit signs and symptoms of the disease. It's a severe enough disease that you would know if you had it. So our patient, whose brother has the disease, does not show signs and symptoms of the disease, so they're not here. But our patient could be, where'd my green marker go? Our patient could be normal normal, so no risk to his progeny. Or our patient could be mutant normal, which could be a risk to his progeny if he has a kid and his spouse also is, say, a carrier. They could have a kid with CF, with the disease. They could have a kid that's mutant. So one thing, when people are looking at having kids, one thing that kind of could go into the planning process is to test each of the parents or the potential future parents for carrier status for CF and for other things like SMA, and there are a couple that they normally test for. So our patient wants to undergo this testing. Our patient knows that their brother has CF, which means the parents most likely are both carriers, which means that there is a chance that our patient, the potential future, say, father, is a carrier. Now, we do notice that two of these out of three of these squares that remain are carrier. So carrier, carrier, normal. So that is where our prior probabilities here come from. In fact, in our prior probability, we've already incorporated a lot of information, a lot of perspective about the worldview, the knowledge about the brother having CF, the knowledge about the parents not exhibiting signs or symptoms of CF, the knowledge about how Mendelian inheritance works and how that typically would apply to the inheritance of the CFTR gene and so on. We've included a ton of perspective already in these prior probabilities. So this represents a type of kind of worldview going into this test. Our patient, our potential future father, let's say, knows at this point that his probability of being a carrier is 2/3, his probability of not being a carrier is 1/3. Now our patient wants to be tested for carrier status. This is a genetic test. They would, take a blood draw, run some genetic analysis on it, and get the results back. Now the test isn't perfect. We'll talk about what this means in a minute. But now the question is, if our patient gets this test done and tests negative, what's the negative, meaning the test is saying he's not a carrier? What's the updated probability as a carrier? A lot of people, I think, just their gut feeling would say, oh, test is negative, he's not a carrier, period, end of story, no questions asked. But remember, this is one piece of information, this test, and we have a whole worldview behind us. We don't want to just throw out the entire worldview and go along with what the test says, no test is perfect. Not even really, really good tests are perfect. There's always the chance of a sample swap or something like that, right? So we want to incorporate the information from this test, of course. We want to use this test information to update our worldview, to change the likelihood that we ascribe to being a carrier versus a non-carrier. We don't want to just throw our worldview out and just say, oh, test said negative, not a carrier, end of story. And we also don't want to just ignore the test and say 2/3, 1/3 for all eternity, no matter what happens. We want to incorporate the new piece of information that we had a negative test for CF carrier status, and we want to do it systematically, and we want to update these probabilities, these worldviews, in light of that new information. Okay, so that is our goal. We need to take a quick diversion into this idea. We have a medical test that is reported, and this is often the way these test statistics are reported. It's reported to be 90% sensitive and 100% specific. Now, it kind of irks me to say 100% specific. No test is 100% accurate in either direction, but we're going to say 100%. Number one, because it's pretty darn close to being true, and number two, because it makes our calculations a whole lot easier. So what is this idea of sensitivity and specificity? Well, the sensitivity of a test is its true positive rate. So we would say, given that we know a certain sample is positive for the disease, what's the probability that when we put it through our test will indicate that it's positive? The sensitivity is the ability to pick up a true positive. What's the specificity? It's the true negative rate. It's saying, given that we know for sure that a sample is negative for the disease, we run our test and ask, is the sample negative? It's the probability the test correctly indicates that the sample is negative. So ideally, the perfect test would have a 100% sensitivity. Every positive person put through the test would indicate they're positive. And also 100% specificity. Every negative person put through the test would indicate they're negative. That would be ideal, but in reality, none of these tests are 100% sensitive and 100% specific. Okay, so what do we have? We have the patient's carrier status. Their, say, prior probability of being a carrier was 2/3. And our question is, we want probability of carrier given test is negative. So their disease status is carrier or not a carrier. We're going to just assume that the probability that they're affected with the disease, that they're mutant, is actually 0. It's not like, some complicated reason that they have 2 mutant copies, but they're not exhibiting signs and symptoms. Just 0 chance that they have mutant. So their disease status is either carrier or not carrier, and the test result is either positive, which indicates carrier, saying you tested positive for the quote disease or for carrying the mutation, or negative, where the test indicates not carrier. Okay, so the sensitivity of a test is its true positive rate. Now, if you ever are thinking about which way the condition should go, think of how a lab would set up an experiment to validate their test, to actually get these numbers, sensitivity and specificity. So back up a step and say, if I was a lab technician and I had a test that I brought online, but I don't know what its sensitivity and specificity is, how would I set that up? Well, the true positive rate, what I would do is I would order a bunch of samples that I know are positive, patients who definitely have the disease that we've figured out through other means. I would have those samples sent over, say, blood samples from a bunch of patients who definitely are carriers for CF. I would run those patients through the experiment, through the assay, and I would see what proportion of them come up positive. I know that they're true positives, that these patients are actually positive. and what proportion of them does my test call positive. So I can find the probability my test says positive, given that my patient is a carrier. And I could do the same thing for folks who I know for certain are not carriers, who I know for certain don't have the disease. I can get samples from folks like that I know are negative for the disease, that I know are non-carriers. I can run them through the test and see how many of those the test says are negative, how many of those the test says don't have the disease. That's my specificity. So my sensitivity, the true positive rate, is the probability the test results in a positive, the test indicates disease, given that the patient actually has the disease, given the patient's actually a carrier. And that is 90%. The specificity, the true negative rate, is given that the patient's actually not a carrier, they actually don't have the disease. The test comes back negative, indicating that they don't have the disease, indicating they are not a carrier. So sensitivity and specificity are numbers that we want to be high for a test. The better test is going to have higher numbers for sensitivity and specificity. As kind of a side note, what is the reason for these two numbers in this context? Well, there are a lot of ways to mess up a gene. There are a lot of mutations that can happen in a gene. The CFTR gene is pretty long. There are a lot of ways you can break the gene. And something like 90% of the ways that you can break the gene, 90% of the mutations that you actually see in people that have mutations occur in something like 20 or 25 different locations. So it's much more cost effective to just look at those 20 or 25 locations and see, does a person have one of the known disease causing mutations in any of these particular areas? If they do, then that copy of their gene isn't going to be functional. The protein that it makes isn't going to work right. And they'll be a carrier. But if they don't, if I look at those 25, say, locations in a gene that's maybe 1,000 bases long, and I see those 25 locations are all normal, they're all non-disease, or whatever, whatever. They're all normal for those locations. Well, there could be another location where the gene is broken that's just not one of the ones we looked at. So our sensitivity is not 100% because we're kind of only looking at a couple of spots on the gene. That makes it much more cost effective to do this and much more, effective for use of resources and so on. But we're not looking at the entire gene. And, these days, even if we look at the entire gene, somebody might have a mutation that it's like, okay, this is a strange one. We actually don't know if it causes the disease or not. So, right, so it's not just a cost effectiveness issue. Sometimes it's the science hasn't caught up yet. On the other hand, why is the specificity, say, quite close to 100%? Well, if I look at one of these 20 or 25 locations, and I'm looking for specific mutations that I know cause the disease, if I look here and I see a mutation in this patient sample, I mean, that's kind of a smoking gun. It's like, okay, yeah, I actually saw it. I witnessed that you have this mutation, barring something like a sample swap or something like that. This person's a carrier. So that's why the specificity is 100%, but the sensitivity is not. So these are the conditional probabilities I have. Probability the test is positive given the patient's a carrier, 90%. Probability the test is negative given they're not a carrier is 100%. This also tells me that I have a false negative rate of 10%. In other words, given the patient's a carrier, the test will come up negative. Their gene will be broken in a spot that is not one of the spots we look at, say, about 10% of the time. It's a false negative rate, so sensitivity is the true positive rate. The complementary event, it seems wrong, but the complementary event is the false negative rate. It seems like we just did a double negative, so we kind of kept the truth value the same. But note that positive switching to negative is the outcome of the test, because the patient's disease status hasn't changed, but the outcome of the test changes. That's what gives rise to also the change in true versus false. So for my patient who does have the disease, if instead of a positive test result, which is concordant with their real state, I get a negative test result, which is discordant with their real state, then that's a false negative. And then similarly, my specificity is the true negative rate. For a patient who truly does not have the disease, is the probability the test comes back negative. My false positive rate is when the test comes back positive and it's wrong, when the patient does not have the disease, but the test indicates they do. Now, what is our, where was my question here? If our patient tests negative, what is our updated probability that he's a carrier? In other words, I want to find probability that he's a carrier given that he tested negative. Notice that I have probability of negative given carrier, but I don't have direct access to probability of carrier given negative. Well, this is just kind of screaming for Bayes. I have the condition that I need is like opposite the condition that I have information for directly. So what do? Well, I use Bayes' theorem. Probability of negative given carrier times probability of carrier over probability of negative. Right, this is just Bayes' theorem up here. So I'm looking for probability of carrier given negative. So A is carrier and B is negative test result. Those are my two events down here. Now I know that there are two ways I can get a negative test result. I could be negative and carrier. So the test says I don't have the disease, but I actually do. The test is wrong. This is a false negative. Or I could be negative and not a carrier. In other words, a true negative. I don't have the disease, and the test indicates that I don't have the disease. I can't simultaneously be a carrier and a non-carrier. I can't simultaneously have the disease and not have the disease. These are mutually exclusive. Negative and carrier, the probability of negative and carrier breaks up to the probability of negative given carrier times probability of carrier. That was our multiplication rule for dependent events. Probability of negative and non-carrier breaks up as probability of negative given non-carrier times probability of non-carrier. So these were just side notes. Let's cordon those off so I don't get mixed in with anything. But now, actually, nicely enough, I need probability of negative given carrier and probability of negative given non-carrier. But hey, I have both of those readily available. And I also need what we call my prior probabilities. Prior to this new information about the test result coming in, that I got the test and was negative for carrier status. Prior to that, my probability of carrier versus non-carrier was given by these probabilities. So this represents the worldview that I'm bringing into the system before the test. And these represent the effect of the negative test. Okay, so let's figure out what this is. Probability of negative given carrier. That is our 10% up here. Like before, I won't write these percents. The percents will just divide out. Times my prior probability of being a carrier. Before the test was run, my probability of being a carrier was 2/3. Nicely enough, my numerator, whoops, that should be a plus. I put a times there for some reason. Make sure to correct that to a plus. Nicely enough, my numerator is always going to be one of the terms of the denominator. In this case, my numerator term, probability of negative m carrier times probability of carrier, is the same as the first denominator term. So I just have 10 times 2/3 there as well, plus. And then my second term in the denominator, these are the true negative rates. Probability of negative given non-carrier is 100%. I'll write that as, let me be careful here, I'll write that as 100. I don't want to write it as 1 because my 10 had a 10%, my 100 has 100%. So keeping it in the same units, so to speak. And probability of non-carrier, my prior probability of not being a carrier was 1/3. This was based on my family history and all that we know about genetics and things like that. I guess I can multiply top and bottom by 3, and I can divide top and bottom by 10, giving me 2 over 2 plus, multiply by 3 gets rid of that, divide by 10 gets rid of that, gets rid of a factor of 10. I get 2 over 12, or 1/6. My updated probability of being a carrier after the information from the negative test result is 1/6. And then, of course, given the test was negative, I'm either still a carrier or not a carrier. Probability of being a non-carrier given the test was negative is 5/6, the complementary event. 1 minus 1/6 gives me 5/6, right? My priors, probability of carrier and probability of non-carrier, were 2/3 and 1/3, or about 67% and about 33%, versus about 17% and about 83%. In light of my negative test result, in light of the test result saying that I'm not a carrier, my worldview, my estimate of the probability that I'm a carrier went down pretty significantly. Went down by what, maybe a factor of 4, I think, if I did this right. 4/6 down to 1/6. So it's a quarter as likely that I'm a carrier, but still not 0, right? The test still isn't perfect. So from here to here, this was what the testing negative piece of information got me, right? Now, maybe I could do something else. Maybe I could incorporate a new piece of information, look back further in my family history, or get a different type of test, maybe a more expensive test, or looking at, lots of different parts of the CFTR gene. Maybe that might not be such a great example because if I do another genetic test, I'll be kind of repeating some of but maybe I have some other magical test that has a sensitivity of, 85% or something, and a specificity of, say 90%, and I can do that test as well if I wanted to. And if that test comes back negative as well, then I have yet another piece of information. The 17% might go down to 10% or 8%. Or if that test comes back positive, maybe the probability goes up a little bit, to 25%. So I could imagine, maybe it's stretching things pretty far here for this actual medical example, but in another scenario, I could imagine continuing to get more and more information, continuing to adjust this worldview until it gets either small enough likelihood that I'm a carrier that I'm, happy with that result, and I say, okay, I choose to proceed forward as though I'm not a carrier as far as family planning decisions and all of that, or until that probability gets high enough that, it's 95%, and I say, okay, I'm going to choose to proceed forward as if I am a carrier. I could keep, accumulating more information, bringing it into this worldview, and then adjusting in light of the new information. So this distribution here that's after posterior in time to incorporating a new piece of information, we call it the posterior distribution. So the prior distribution before we have the new piece of information, the posterior distribution after we have the new piece of information, the test being negative in this case. Okay, so here's an interesting exercise. Um, so what if the prior probability distribution was probability of a carrier is 1 in 22 and probability of non-carrier is 21 out of 22. For CFTR mutations, this is about the carrier status of kind of people of European descent um, for having some kind of a CFTR mutation. So about 1 in 22. So if instead, maybe his brother doesn't have CF, nobody in his immediate family, siblings, parents, whatever, have CF. For a patient like that, this might be their prior. And then when the test is negative, if the test is negative, what is their posterior distribution? And then if the test came back positive for a patient like this, what would their posterior distribution be? Here are the answers, but go through the computations as an exercise and see if you can come up with the same answers. One thing that you will note is that a negative test result indicating they don't have the disease, when it's quite unlikely initially that they do have the disease. So kind of the worldview is you probably don't have the disease. We get the test says you don't have the disease. Now we're like pretty darn sure you don't have the disease. 5 parts in 1,000 or 1 in 200 chance that you have the disease. If we look at this, getting a positive test result is a guarantee that you have the disease. That seems awfully a lot like we just threw away our entire previous worldview about everything and just went with the test result. We kind of didn't incorporate the worldview at all. We just said positive test result, you definitely have the disease, no questions asked. I don't care about anything else about family history or anything like that. Is that a good result? Probably not. Where is this coming from? It's coming from this 100% that we like hard coded into here. So if you want to really take this even a step further, rework this, but with, I don't know, 99% specificity and then 1% false positive rate and see what effect that has. So if you want to take it even a step further than going through these exercises, do that. What if the specificity was 99%? How would that change this answer? And that's kind of the cautionary tale of putting 100% or 0% for probabilities into models. We generally don't want to do that because we end up with things like this, where we just kind of threw out the entire previous worldview in light of the test because we're, in essence, claiming that the test is perfect in a certain direction. And of course, no test is going to be perfect, really ever. Any questions on this example? Okay, let's look at example 2. So here we have an example dealing with mammograms, a screen for breast cancer. This has a false positive rate of 86.6 out of 1,000 and a false negative rate of 1.1 out of 1,000. The prevalence of breast cancer in the population that gets mammograms. So the prevalence being, if you took somebody from this population, randomly chose them, what's the probability that person has breast cancer? It's 1 in 38, about 2.5%, right? About 1 in 40, 2.5%. Let's find the so-called positive predictive value of the test. That is, in other words, the positive predictive value. So how well does a positive test result predict positive patient status? In other words, patient having disease. We want to find the probability the patient has breast cancer given that they tested positive, given that their mammogram was positive. Well, we have a false positive rate of 86.6 out of 1,000. False positive means, well, the test came back positive. Remember, the test result is the thing I can see. I can't like if I'm the doctor or even if I'm the patient, I can't omnisciently see whether the patient has the disease. If they did, we wouldn't be talking about probabilities. We just say you have the disease or you don't have the disease. So the thing we can see is the test result. So false positive rate, that means I saw a positive test result, but it was incorrect. Right? Again, how would we get this number? Well, we take a bunch of known positive people, run them through the test, see how many of the test calls positive, and then we would do the same for known negative people, run them through the test, see how many of the test calls negative, and that's how we get these numbers. So the test has a false positive rate. In other words, probability the test is positive, indicating disease, given the person does not have breast cancer, given the patient's actually negative for the disease. That's what's 86.6 out of 1,000. Now, what's the complementary event to this? The complementary event is changing positive to negative, but keeping the population the same. Here we're looking at the population of folks, of the age and gender and so on, sex that gets mammograms that do not have breast cancer. Those folks can either come up positive from the test, from the mammogram, or it can come up negative. So that is the complementary event. Probability of negative given no breast cancer is 1 minus this, or 1,000 over 1,000 minus 86.6 out of 1,000. That's 913.4 out of 1,000. Probability of negative given no breast cancer. The patient is negative, the test is negative. That is a good result. That's a true negative rate. That's the specificity. Right? A high specificity means the test is very specific, that it's not going to pluck out people who are negative and call them positive very often. A high sensitivity, like if you say, like your fingertip is a sensitive part of your body, if you're running your fingertip over a flat surface and there's a little, grain of salt or sand or something on there, since your finger is very sensitive, you're going to find it. If it's there, you'll find it. So a high sensitivity means if the patient has the disease, the test is highly likely to find that to result in a positive. So you can just think of the word specific and sensitive, like how we would use them colloquially. And that also gives a pretty good hint into which one goes which way. So what were we told? We're also told that the false negative rate is 1.1 out of 1,000. So this means the test came back negative, but was incorrect, meaning the patient had breast cancer or has breast cancer, but the test came back negative. That's what's 1.1 out of 1,000, probability of negative given breast cancer. And then the complementary event, probability of positive given breast cancer, is 1 minus that, 998.9 out of 1,000. That's the sensitivity. And what we want to find, of course, what we're interested in is, given the test is positive, what's the probability the patient actually has breast cancer? So if a woman goes in, gets her mammogram, comes back positive, is it like, almost a certainty that she has breast cancer? Is it still pretty unlikely she has breast cancer? Is it like moderate 50-50? What's the probability of her having breast cancer given this new piece of information? The mammogram was positive, right? Started out at like 2.5% chance. A positive mammogram is going to increase that likelihood of her having breast cancer, or her subjective estimate of the probability she has breast cancer, but by how much? Again, we don't want to just throw out the whole worldview. This isn't a disease of very high prevalence from an absolute number. I mean, relative to other potential diseases, it kind of is a high prevalence, but from an absolute number, 2.5% isn't very likely. We don't want to just throw out that perspective and say, positive mammogram, definitely have breast cancer. That would be a little too flippant, or way too flippant. We also don't want to ignore the positive mammogram and dig in our heels and say 2.5% forever. So how do we incorporate that systematically? Again, we look at Bayes' theorem. We want probability of positive given breast cancer times probability of patient having breast cancer over probability of a positive test result. And just like before, there's two ways to get a positive test result. It could be a true positive or a false positive. So a true positive would be patient has breast cancer and test is positive. So probably a positive and breast cancer. Well, that's probably a positive given breast cancer times probably breast cancer. And the other way we could get a positive test result is a false positive. This would be, well, test is positive and patient does not have breast cancer. So probably a positive and no breast cancer. Probably a positive given no breast cancer times probability of no breast cancer. I know the prior probability of breast cancer is 1 in 38, and the prior probability of no breast cancer, 37 out of 38. All right, so let's fill these in. Probability of positive given breast cancer, that is this one here. I'm not going to write all of these over 1,000s. We're going to have one here, and one there. Those will just essentially multiply top and bottom by 1,000. Those will go away. So this is going to be 998.9 for probability of positive given breast cancer without the over 1,000. We get another one of those in the denominator. Probability of positive given no breast cancer. The other way I could get a positive test result, 86.6. And maybe I'll switch colors here. And then my prior probabilities, probability of breast cancer, 1 in 38. I'll just write that as a 1. Same thing on the bottom here, probability of breast cancer, the prior probability, 1 in 38. And then probably a no breast cancer, 37 out of 38, I'll write as a 37. Again, I have this kind of countervailing powers here, right? If the mammogram comes up positive, it's pretty darn specific. Its likelihood of being a false positive isn't very high. So if the mammogram comes up positive, like in some sense, it's probably kind of right. But in another sense, well, actually not a lot of women have breast cancer, who are just going in for a screen and don't have signs or symptoms, right? So I have kind of a low false positive rate, but kind of a high true negative rate. Maybe I shouldn't have said it that way. I have a low false positive rate and kind of a high underlying negative rate versus a really high true positive rate versus a pretty low underlying positive rate. So I have kind of a and these are real life numbers, like both in example 1 and example 2, real life numbers. This, I don't remember, this came out of a peer-reviewed journal article. So, I mean, that's where these numbers came from. But this is basically this same scenario here, right? I have like my underlying numbers versus my conditional numbers. One is high versus low in one direction. The other one's high versus low in the other direction. That's exactly what we see here. And if I compute this, what do I get? Equals, I have a numerator, 998.9 divided by my denominator. Better put this in parentheses, 998.9 times 1 plus 86.6 times 37. And the parentheses, that looks good, gives me about 24%. So my priors, probability of breast cancer about, let's say 2.5%, 1 in 40. Probability of no breast cancer about 97.5%. So when the woman walks into the mammogram room or before it's read and gets the results back, kind of her estimate of having breast cancer, the likelihood having breast cancer, 2.5%. the posterior for a positive test result, given that she gets the result back from the mammogram and it says your result was positive for some type of dysplasia. But we're also just kind of saying breast cancer, no breast cancer, not like high grade dysplasia or like DCIS or any of these other, kind of cancer like things. We're just obviously keeping it overly simplified for our discussion here. But the posterior probability of breast cancer given a positive test result is about 24%. And of course, given a positive mammogram, the probability of no breast cancer, that's the complementary event, about 76%. So even for a woman going in and getting a positive mammogram, it's still like a 3-to-1 ratio against her having breast cancer. Even with a positive mammogram, it's still much more likely that she does not have breast cancer than that she does. However, the likelihood of her having breast cancer has increased by a factor of 10, right? She started out as it being extremely unlikely that she had breast cancer, and now it's kind of like pretty unlikely, but not extremely unlikely anymore. She's definitely going to want to follow up, get it checked out. 3 out of 4 of those follow-ups are going to result in the physician saying, nope, you don't have it. Like it was false positive from the mammogram, looks all good. And 1 out of 4 of those, is not going to be so great. So we might ask then, I mean, this seems a little silly. Why so many false positive? I mean, we have a test that said they came back positive, kind of indicating disease, but still the odds are pretty well stacked against the woman actually having the disease. And that's not just trivial, that's costly, right? I mean, that's a period of time where it's going to be super stressful. There's more invasive testing, more follow-ups, more financial expense, more use of healthcare resources. It seems a little silly to do this. Why don't we fix this? Why don't we have, let's say, why isn't our 998.9 bigger, or our 86.6 smaller? Well, there's kind of 2 answers, or 2 parts to this answer. One is that there's a trade-off. I mean, it would be super nice if we could just always drive sensitivity and specificity both to 100% and drive our false positive rate and our false negative rate to 0, right? If I could drive this to 0, if I can make this 1.1 out of 1,000 as well, hey, that would be great. We wouldn't have nearly as many false positives because our false positive rate would be so much lower. But the problem is that, practically speaking, that's hard to do. I can drive false positive rate down, but the way that I do that is by calling fewer positives. If I'm the radiologist looking at the mammogram, if I see something suspicious, but I'm not really sure, I have to decide, do I call it positive or negative? For a screen for cancer, the bias, for good reason, is going to be towards positive. It's probably better in most cases for the woman to spend, a couple weeks or a month a little bit stressed out, go in for a follow-up that's, maybe kind of uncomfortable or annoying, and then find out she doesn't have cancer. That's probably a better result than saying, oh, you're all clear. She doesn't get a follow-up, and a year or 2 later, she finds out that she had cancer that's been getting worse and worse, and increasing in stage and severity for a couple years. That's probably the downside of that scenario is probably much more costly than the downside of a false positive. Now, I mean, there can be debates on this, of course, and a lot of people have debates about, what are the severities of these downsides versus their likelihoods and so on, and where do you kind of draw that line, right? Where does the radiologist draw the line between saying, this suspicious, so I call it positive, but as a kind of a general rule, they're going to be more likely to call something positive on a screen than negative if it's in a gray area, because it just kind of feels better to do a little bit of extra testing versus, missing a disease that could end a person's life, right? Um, so that is what's kind of going into here. There's a trade-off. The radiologist can't, you can't just say, okay, radiologist, just be better. Like that's not something you can practically do. It's the question of when it's in the gray area, which way do we bias the call? And we bias it towards calling it positive, towards getting a little more follow-up than over missing actual disease and letting it progress for a year or two and get much worse. So that's kind of the reason for this. Now we could, in theory, drive both of these numbers down. We could, in theory, get better specificity and better sensitivity. But to do that usually requires something fundamentally different. So maybe say better technology. If we have better imaging, like just X-ray machines that actually just work better and give a clearer picture to the radiologist, maybe that would allow them to make better calls, right? So over the years, as technology increases, these numbers can get better. Or the other thing is, well, radiologists are humans that have to make a decision. Well, what if I had two radiologists look at every image, and when they both agree, we make that the call. And when they disagree, when one person says positive, the other negative, we have like a tiebreaker, third radiologist come in. I think they might do this in some European countries. Well, yeah, so that would probably increase sensitivity and specificity. It would probably make it a more reliable test, but now the test is more costly. And we want this to be accessible to everybody. So now healthcare is more costly, right? So there's a trade-off there as well. So if we have maybe better technology or we're willing to invest more money or whatever, we might be able to kind of drive both of these closer to 100%, but we can't just, it's kind of like, we're placing a cutoff bar. We get to move it left or right, but we can't like move it in both directions at once. We can't tell the radiologist like, we want you to avoid missing disease, but we also don't want you to overcall anything. They're going to tend to overcall it. So that's the reason for this discrepancy. And in fact, this is pretty standard across anything that's a screen. Anytime that you go to a doctor and you say, I don't have any signs or symptoms, I don't have any good reason to suspect I have this disease, but we're going to get screened for it. If that screen comes back positive, it's probably still pretty unlikely you have the disease. That's just an indication for maybe some follow-up and, some more expensive or whatever testing. Okay, so next time we come back, we'll work through this kind of Bayesian machine learning example about insurance and car insurance rates and so on. And oh, my other windows didn't copy over correctly. So, well, good thing that's next time. So that will be next time. That'll wrap up the Bayesian discussion. And again, supplements posted on Blackboard. So definitely take a look in the supplemental materials folder in the, I think it's chapters 4 and 5 folder. In there's kind of a write-up of kind of this discussion about Bayesianism and some other examples and practice problems and things along with some answers. So if you're and one more thing, I just want to make sure that we're clear, like you don't have to know genetics, you don't have to know like Punnett squares or any of that. Like that's not that was just background that I thought some of you might find interesting if you're going into a medical field or if you've seen some of that stuff in your science classes. Let me stop the recording.